In the last lecture we discussed about two kinds of platforms, that is, one is the fixed template structures, the second one was the articular towers, where we had discussed about the ATs, then multi hinge towers, then multi leg towers, and the literature by and large showed that these towers have lot of quick recentering abilities, which actually causes lot of displacement to the top hull or the top side, and response control of these are mandatory if you really wanted to use them for production and exploration. Otherwise they can be used as an anchored systems, which was generally one of the functions for the pipeline support system or one of the temporary ways for inspection and repair. But if you really wanted to use them for exploration and production, then one should control the top responses. So one of the interesting idea which was conceived by the researchers in early 90s and 2000 were the response control using passive dampers, where we picked up one of the model of the passive dampers, where we used the tuning of the secondary mass to the primary mass system, and we showed that how the control equation with 7 variables can be reduced to optimization problem of 4 or 5, and then we showed you that how that dynamic amplification factor at omega equals omega n gets modified with the successive adjacent peaks, but the value is, the amplitude is slightly and relatively lower, which resulted in about 10% reduction in the surge response and about 7% reduction in the heave response, attempted on a scaled model of one kind, where the top side weight was approximately 2500 tons for a different mass ratio, where we call M2 versus M1 etc. For we have showed you the studies and how it was done. So we verified the whole concept experimentally, analytically and numerically. Then we showed that how the tuner mass dampers can be one of the effective method by which I can control the response, essentially using the principles of dynamics. So we used it as a design philosophy, and we solved the equation of motion and optimization problem indirectly by choosing the secondary mass ratio with respect of the primary. So we call this as a tuned mass damper system, which is one of the passive dampers which are commonly used for buildings, but it was a very novel application for offshore structures for the first time. Then as we move on to, let us say, the conceptualization of offshore platforms, we know and we have studied in the first module that they have started from the shallow depth to medium to deep waters etc. The conceptualization essentially focused on the design concepts. Initially they were focused on a structure which should remain insensitive to wave action. That is what people conceived as an idea for design of offshore structures. So they came out with, let us say, template structures, gravity based platforms etc. But they found that the initial cost of construction, then commissioning of the platform, and on the other hand decommissioning etc. became very expensive, and it involves lot of time, for about 7 to 10 years to conceive a platform for production, and the platform require lot of repeated attention, so that they get corroded because of steel, which is essentially used major as a template structure in jacket leg structures. And because of GBS there were other parallel problems and geotechnical issues, where there has been soil liquefaction, rocking phenomena occurring in the foundation etc. So the idea of making it insensitive to water depth, which was conceived in the beginning for the design, was found to be a failure, because though it was successful in terms of its application, but it had got other parallel socio-economic effects and environmental effects. Therefore people then moved on to conceive this idea for medium water depths, where they said let us make the structure compliant, make it flexible. So, when they want to make it flexible, then they found a feasibility of moving this platform from shallow water to medium water depths, let us say up to, let us say 500 meters, and they introduced guide towers, articulated towers, multi legs, multi hinge, etc., where we have been all using them for medium water depths up to 700 meters, 600 meters, where there is a semi compliancy involved in this. But again in this case the topside responses were phenomenally high. So, people could not use them for production and exploration, and the topside detail available in terms of its size, equipment detailing were not as comparable to that of these kind of structures. So, people said okay, this idea is also not good, and immediately the exploration also moved on to deeper water depths. So, people then came out to purely compliant systems. So, initially they were semi compliant, purely compliant systems, and the first concept which came in mind in 80s was actually tension-like platforms. Though there are many papers, many literature available to conceive the idea of TLP design and dynamics, etc., but in this lecture and couple of lectures we will try to explain you how TLP idea was conceived as a design philosophy and how dynamic analysis can be done for a tension-like platform experimentally, and we will also talk about something called geometric optimization of a TLP. I mean why and where we can do a optimization for geometric design, where is the necessity for this, we will talk about this. So, this will be an interesting area which is new and relatively appreciated in the literature in the recent past. So, we will talk about this. So, the moment we say tension-like platform, then the idea actually came out with a different philosophy in terms of its design. The foremost focus in this concept was installation. One can even say fabrication, one can even say commissioning, etc. But the initial focus was installation. I mean people wanted to make it installable, free, and with a main focus in installation as reusability. I mean I want to have a portable platform. Essentially I want to move the platform from location A to B, B to C, and so on and so forth without much effort, which were not possible at all in any one of the earlier conceived ideas, completely new. So, it was drastically a off way of thought process in terms of design of offshore platforms, where people wanted to make it totally mobile. But remember, in all these through years from 60s or maybe even 20s till 2000, you will need parallelly naval architecture was also a parallel trade, where shipbuilding was essentially growing in a very rapid state. Essentially not in India, but in many developed countries shipbuilding industry was in a very great progress. So, they had a very good idea about how to handle a floating vessel of a very large size, maybe even for a warship, even for cargo handling, etc., in terms of how to maneuver them, how to design, and therefore they could have easily anchored that very ship and convert the ship to an offshore platform. But that idea was not conceived till 90s. Drill ships came very late in idea. Even today drill ships are used only for exploratory drilling, not for production, because it is very expensive to hold down a ship of that order compared to its economic viability in terms of sailing it for commercial value. So, people do not use it. Only the ships which are non-sailable are then altered to made as a drill ship. Even today that is a fact. Okay. So, people never conceived this idea in terms of design concept for a platform. People always thought platform should remain stationary, but reusability and somewhat high degree of compliancy, not mobility. Mobility in sense they want to move the platform from A to B, but they never wanted the platform to remain in motion while drilling is in operation. So, ship idea was never conceived. Okay. So, there is a drastic difference in dynamic analysis between that of a floating bodies to that of a fixed bodies. That is where the difference is. One may easily understand that if you know dynamic analysis of a floating body, can't I design a compliant vessel? No, because compliant vessels do not float. They are taut mode, they are position restrained, that is where the maximum difference comes into play in dynamics. So they wanted to make it position restrained. One can ask me a question, why a system should remain position restrained? Even if you want a drill ship to be used or a ship to be used for production, you have to have essentially the drill well which is identified, and you have got to do an exploration. The risers are connected, therefore the risers do not have high degree of flexibility in terms of its length adjustment except marginal. Therefore your vessel which is meant, or your platform which is meant for production, even exploration, should not move by and large in a large way. So they should remain position restrained. The moment they position restraint is a focus, they also wanted to make it compliant. Then these two objectives were met simultaneously with the synchronization of holding down them using mooring lines. There are two types of mooring lines. One can have a catenary mooring profile which is completely slack mooring, which is a slack mooring system. Other one is a taut mooring system. Slack mooring system is generally deployed for holding a vessel of a large size in position, provided this vessel is allowed to move in a large displacement, but does not want to get offloaded from a point. Whereas taut moored systems are generally used in a place where you want to remain or retain the vessel position restrained, and taut moored systems will always limit the displacements. So there is a fundamental difference in behavior between a large vessel which is floating, between a large platform which is position restrained. Therefore the dynamics applied here will not apply here as well, because as we all understand from the fluid structure interaction to a by and large way, if the vessel or the body is allowed to move in a large dimension, it will cause secondary vibration like VIV etc., which does not happen in this kind of vessels or platform because they are predominantly position restrained. So people opted for a taut mooring system. So they gave a new term to this as teethers, tendons. Tendon is a term which actually borrowed from bridge engineering. A typical style of cables are used in bridges for pre-stressing, they are called tendons. So this has been actually borrowed from bridge engineering, because in early 80s or late 70s bridge engineering was in its peak in infrastructure development all over the world. So people have used pre-cast, pre-stressed constructions where tendons have been used. So they have borrowed this terminology. In fact, high yield strength deformed bars with high initial yield strength values have been actually started used in offshore structures only after they were successful in bridge engineering. Okay, so that is the idea why they have borrowed the terminology also from there. So tendons are used. Of course they have named as a teethers. So tensionless platform was the first idea conceived, maybe in late 80s or early 80s. We have got a very long history. I already given you the history, what are the platforms constructed in the world elsewhere, TLP etc., even till today. We are not looking back to the history, but let us see what are the concepts in the design. So let us say I have a body usually rectangular in shape, let us say a block. Let us say I have a solid block, a wooden block let us say. Obviously when I want to make it completely submerged, it will not have buoyancy. If it is completely floating, it is no use for me, because I have to position and restrain this. So I have to have a partial submergence. Okay, it has to partially submerge and partially be above water. The moment I say partial submergence, the volume of immersion or wetted surface area will play a role, which we all know by Archimedes principle. This will apply a vertical force which we call as a buoyancy force. Buoyancy force is actually proportional to the submerged volume of the members. Now we all know that this cannot be a solid block, because I have to have lot of operational features on the top. So people converted this into columns and pontoons. These are called columns. And these are called pontoons. So these are called pontoons. These are called column members. And we all know that the moment you allow the member to remain transparent to waves, we already saw in fluid structure interaction in the earlier lectures of this module, when the wave passes through, then the obstruction caused by the member, if it is minimum, then the force exerted on the member is minimum. If the wave is obstructed by the member, then it causes a lot of secondary force like diffraction, radiation, etc. We saw them in detail in FSI earlier lectures. So, with that idea conceived in mind, people said, okay, between the columns and the pontoon, let this area remain hollow, let the wave pass through. The wave passes through, then the forces on these members are minimum. Okay, that idea was conceived, it is very easy. So, now I have a body which is not solid, but I am focusing only on excessive buoyancy. The buoyancy will appear only when I have got a large surface area, it does not bother about the weight. I want to have the submerged volume should be larger. Okay. For example, to be very specific, I have a cylinder whose diameter may be 100 millimeters. I have a cylinder whose diameter may be 200 millimeters but hollow, maybe a tube. The amount of submersion is solid, this is solid, this is hollow, this is a tube and this is a solid cylinder. The amount of submersion of both the cylinders is same, let us say X or H. In that case, you will obviously see, since this diameter is larger, though the submerged height is same, the volume of water displaced by this member will be much larger than this. Okay. So, I am talking about actually buoyancy. So, with this idea, people had large diameter columns and large diameter pontoons and made them hollow. The moment you made the structure hollow, structure actually lost its weight because it is hollow. Okay. Now, weight has come down and buoyancy has gone up. Okay. Because large diameter sections, weight has come down. There are two reasons for having large diameter structures. One, large diameter members because excessive buoyancy. Large diameter members because this inside space can be used for some storage also, can be for ballasting, can be for oil storage, many purposes can be met. Okay, if one wants to, because this idea was not new, this was used in buoyancy chambers, in ATs also, in guide towers also, people have used this idea. So, the same idea would definitely have an effect on this conceivement of a new concept when it grows. Okay. So, people said let us have a large cylinder of hollow in size or a tube, but I have members of a larger diameter, but since the structure has become completely transparent to waves, of course, the top is solid because I have a lot of topsy details here. So, it is solid, it is a deck, maybe not a single deck, multi-tier deck. Of course, the bottom may not have anything except that there can be a moon pool through which the riser goes through and rising or the drilling operation takes place. Okay. Now, with this concept conceived, weight has come down drastically because you have made the system wave transparent, but buoyancy has gone up drastically because you are using large diameter column members and pontoon members. So, the idea is now buoyancy exceeds the weight by a very large value. Now, this has got a very great advantage. What is that advantage? The advantage number one, which is foremost, is when you have any system whose buoyancy force exceeds weight, the system can remain afloat. You do not require any energy to move the system or float the system, which was originally the idea. Okay. Now, they want to make installation free, therefore, the system can remain afloat because of this characteristic. Okay. Number two, the moment I have a system which can remain afloat, I can always prefabricate the system in modules and bring it from a workshop and float it to my site. Whereas in earlier cases, the structures were built in module, they were brought in vessels, special cranes were used, the cost of installation and construction and fabrication becomes very expensive because you are doing the entire installation on sea under a specific weather window. But in this case it is not so, it is like a vessel. Well, one can ask me a question, how people were confident in an idea of bringing a vessel or a structure or a platform or a module which is very large in size but remains afloat. This idea of engineering was borrowed from naval architecture because people already had this idea of floating very large vessels in terms of ships. They can float from any area to any area because they had this idea. Okay, the design idea was there, conceptualization of installation and fabrication and commissioning and maneuvering were already present for about 100 years with ocean engineering team. they have used that idea, conceptualized the design, had a design of buoyancy exceeding the weight. Now when you look at the whole equation of equilibrium, the whole platform will have its weight which is acting W. Now since Fb which is acting upward and W acting downward need to be equal, because then only it can remain in equilibrium, otherwise the system will always have a tendency to push up. Okay. There should be something which has to bring it down. Okay. That was nothing but T, which is called the axial tension in the tethers. So now I have to put a cable or a tendon or a tether or a taut mooring line to all the columns and anchor it to the sea floor by special arrangement which were same as that of guide wires or guide towers used earlier, where you got a touchdown point, where people use drag anchors, all were available here as well. The idea was borrowed, and now you will obviously see they all will be in tension. We all know how to mark tension in an axial cable. It is always marked with respect to the support. Okay. So they are all in axial tension. I call this specific value T as initial pretension. The moment I say pretension, then one can conceive an idea as an engineer in mind that tension is applied or pre-applied to the cable. Now one can see here where the tension can be pre-applied, because if you have got to apply a pre-tension to this cable in C, somebody has to go down and pull. Okay. Or there are top tension tighten risers, TTR systems are available, where you can make it roundabout and pull it on the top, but still when you are pulling a cable of a very high value, you are pushing the system also. You have to have a reaction. If you want to pull something, you have to push something. Okay. So it is very difficult to have such a mechanical complication, because that will add complexity to my installation and fabrication. So people thought what can be best done. The best done is, people said, initially I will say I will ballast the system. So all these columns members and pontoon members which are hollow inside were used to fill up ballast material, essentially water, because they can be taken out easily. So initially you ballast. When you ballast them, weight actually increases. Okay. When weight increases, platform comes down beyond a design draft. There is a design draft for this platform. Maybe if this is L or H, maybe this is X bar or H bar. There is a design draft for this platform where this is maintained, okay, for the design draft. But when you add ballast, weight will increase, the design draft will come down, the platform will come. Maybe if you keep on adding more and more ballast and more and weight at the top, the platform may even completely sink also. Okay, there is a possibility, because you can make W to also exceed or equal to Fb without T, that is also possible. Keep on adding weight, it will sink. Okay. So keep on ballasting them, attach a cable here, all these 4 points, and keep on adding ballast. So the cables now will be all slackened, they all will be free, is it not? Okay. So the divers can go down, anchor it to the pile foundation, specific location, tighten them. Once they are ensured they are tightened, you deballast it. The moment you deballast it, because of the buoyancy force will try to push the platform up, that will automatically impose pretension to all these tethers. Okay. So that is why it is called tension leg platforms. All legs will remain in tension all the time, There is no question that at any service time in a TLP, these tethers will again slacken. Why? Because they are not tension imposed, they are pre-tension imposed. Tension is already there. If you are not having tension in the platform, you cannot commission the platform at all. So and this value is very, very high, because I said buoyancy is excessive by large number than W. Therefore this compromise has got to be done only by T0. If I call T0 as my initial pretension per leg, I can always say multiply this with 4, because there are 4 legs. Okay. And each leg can contain different material or different configuration of tethers. Maybe tethers can be of a solid core, each may be having group of tethers, maybe 6, maybe 8, maybe 12, depending upon what kind of platform. If you look at the history of how platforms were erected and commissioned, Auger TLP, Hutton TLP, etc., you will see the group of cables and each leg can vary anywhere from 3 to the top 12. So, I am not talking about a single cable, I am talking about a group of cable. The yellow line represents here is nothing but this. Okay, each is a group. Okay, again one can ask me a question, how they will be arranged, how they will be all interlocked, how they can be pulled together, how they can be slackened together. The whole idea came again from bridge engineering. I can give an example. Fresnel is one of the style of processing in bridges, where people have used multiple cables of this order and tried to pull them together and release them together. It is an idea in bridge engineering. So, the same concept similar of this order has been used here, but our unfortunate part here is you are not applying any end bearing forces here like in bridge piers, because here tension is automatically imposed only by ballasting and deballasting the platform. So, large buoyancy of large diameter, hollow space have been used in erection, all concepts became advantageous in terms of its design conceivement for a TLP. So, TLP idea became very popular and TLP started getting commissioned, and the installation time from 10 years to 7 years came down to just 2 years. So, drastically the construction time, or let us say the time taken for producing oil from that of the field identified came down drastically, and economy improvised very fast. In Gulf of Mexico many TLP sequentially were constructed. Okay. Reusability, we will talk about this slightly later. Once we talk about the stability of the platforms, then I will tell you how reusability can be done. Now, if you can easily think, if I really wanted to reuse this platform from location A to location B, where A initially had oil exploration viability, but it has got exhausted, I want to move it to a location B which is few kilometers away from here, where I cannot do drilling from here itself. What all I have to do is simple, I have got to release these pre-tension cables. Obviously, since the pre-tension is very high, I cannot simply think of releasing them just like that. If I cut them, it will cause lot of secondary vibration, it will damage the whole platform itself. So, I have to again ballast it, release the slackening of the cables, then cut them, deballast it, the system will become afloat, move it. So, it is very easy conceptual wise, though very difficult to execute it, but possibility was there. Okay. So, decommissioning, fabrication, reusability, installation all came into play powerfully with great advantage of using a TLP as a concept. Okay. Now, if you look at the equation of static equilibrium, that is at any given point of time when the TLP is not in motion, then it should be satisfied. Where I say T0 is the total pretension in all the tethers. Okay. This is equal to static equilibrium. Any point of time this should be satisfied. Okay. Now, when you talk about dynamics, as we know that is my classical equation of motion for a given system, which is multi-degree. If it is multi-degree, then these are all matrices, these are all vectors, and we already have worked out in detail how to find out f of t using different wave theories and different spectra for finding forces. We already know the right hand side of this equation. Whatever may be the structural system, I should be able to divide them into finite elements and try to find the forces because of the executed by the water particle acceleration velocity on the member, and from that I can find the forces. Either I can use diffraction theory or I can use Morrison equation, etc. I can find the force in each member, I can accumulate them, I can rearrange all the forces in the total 6 degrees of freedom, I will get a full vector which I can easily. So, right hand side is not a botheration for me as of now. Now, the question here is, in this case displacement, velocity and acceleration are my unknowns because they are related to structure. Okay. In the earlier case it was not very serious because they were actually not getting displaced at all. Okay. In this case they are very serious because we are talking about a compliant system where the displacement is very high in order. So I have to solve this equation of motion to give me the structural displacement. So I must know all these matrices first, let us say the stiffness matrix, the mass matrix and C. How the matrices of this order are different from that of the earlier structure is the beauty. This is where the design idea became into a difficulty in dynamics. Many papers will not detail talk about, except that V.J. Kurian etc. in early 70s came out with the concept of explaining how this can be derived. Very seldom papers in literature review will give you a detailed explanation of how to derive the stiffness matrices, very difficult, you will not find these papers, though stiffness matrix derivation is actually a elementary lesson as far as structural mechanics is concerned, but many authors did not actually give that in detail. You will find most of the papers do talk about analysis, dynamic analysis, results, RAWs, response amplitude operators, response control, geometric optimization, all about TLPs. There are more than about, I think for the past 20-25 years there can be a lot of conceptual papers in TLP. Even today TLP engineering has gone to that level. Even good congress like OMAE, like ISOP, ASME, they all have dedicated sessions, parallel sessions on TLP alone. It has become to that, it has become a domain of engineering now. Okay, so that extent has grown and it has been proved to be very successful up to a depth of about 1200-1300 meters of water depth. People have used commission platform successfully. Now it has been a proven concept that TLP can be an established model for oil exploration to deep waters. No second thinking about it. So people are dedicating lot. Now people now talk about stability, reusability etc. and how to improve the performance of a TLP for greater water depths etc. One greatest advantage what TLP had vis-a-vis all other platforms so far till 80s is that when I talk about this as my water level, this is my design draft, this is my water depth, let us say small d, and because capital D indicates the diameter, capital D will indicate the diameter, therefore small d will always indicate the water depth. Okay. So this is the water depth, this is my design draft, I call this H bar. So you will see that except for a small fraction of that of the depth, the whole volume has no material investment. Whereas if you look at any other platform prior to this, the whole volume of material was invested in this segment alone and it was only 20% above. So it was just a swapping concept. So people immediately saw a very good economical perspective on installing a TLP. Okay. So that is the idea. And to have a thumb rule, people started with this understanding that the pretension in the cable will be approximately about equal to 15 to 20% of that of the weight in each leg. Okay. That is the idea, that is the overall thumb rule. We will talk about that in details later. So every good congress started having dedicated sessions on TLP, and TLP engineering has become a great sign of promotion in offshore industry for deep water oil exploration, production, processing etc. Because the top side was as similar to that of any other platform. And to give an idea, you may remember maybe a Mars TLP has a size of about 80 meter one side. So it is very large in size, okay, very large platforms. You can look at the geometric and structural configurations of different TLPs available in the site from the open domain or any papers listed in the NPTEL, you can see them, but nevertheless no TLP had any body dimension less than 66 meters. It was a very very big platform like a small township, okay, it is a very big platform in size. So they have got a very good concept and it has been established. Now let us talk about derivation of, let us say, elements of equation of motion. Let us take the first element as the stiffness matrix. So, let us quickly see how do we derive a stiffness member of a stiffness matrix. So, if I say Kij, because small k will indicate member of capital K and capital K is actually the full matrix. It is nothing but the force in ith degree. I am using degree of freedom as DOF, ith degree for unit displacement given in jth degree. Okay. Keeping all other degrees of freedom restrained. Just have a quick resemblance. We must recollect that how we generally do a stiffness matrix derivation for a beam element, because you must have already studied in structural mechanics how to derive the stiffness matrix for a beam element. At least one value we must remember. Okay. So, if I have a beam which is fixed at both the ends, the beam has got length A, L, A, E and I are the properties. I moment of inertia of cross section, E Young's modulus of the material, A area of cross section, L is the length of the member from the supports or between the supports. I must draw the degrees of mark the degrees of freedom for this. One can ask me what is the degree of freedom at these two joints. It is actually 0, it does not move anywhere, okay, because this joint neither allows displacements nor rotation, this joint neither allows displacement nor rotation. The degree of freedom for this beam at these supports are 0. Okay. So, let us mark the degrees of freedom first. Let us say degree 1, 2, 3, 4, let us say 5, let us say 6. I have marked 6 degrees of freedom on a 2-dimensional plane. I am not talking about the 3rd dimension, okay, 2-dimensional plane. So, let us take up any one specific degree and try to find out what are the forces in all 6 degrees if I give unit displacement 1 degree, and see, that is how I will get the first column. So, the stiffness matrix is always derived column wise. So, stiffness matrix is always derived column wise. So, let us pick up this beam again. I want to give unit displacement about the first degree. So, I give unit displacement. Let us say this displacement delta is unity. So, this is my beam profile. You may ask me a question immediately, why I am drawing a profile like this. It is very simple. I have to impose that when I give unit displacement in the first degree, I have to keep all other degrees restrained. It should not move anywhere. So, I am posing them back. Obviously, when I have a displacement of this order, this will always generate a moment. Okay. So, the moment is marked this way. One can ask me a question, how this direction has been fixed. Okay. Since it has moved up, bring it down. Had it been moved down, had it had moved down, bring it up. Had it had moved to the right, bring it back. Had it moved to the left, bring it back. So, you have to assume the arrow direction in such a manner that you bring it back to normalcy, that is the idea. There is nothing like anti-clockwise, clockwise here, bring it back. Then one can immediately have a doubt, why we have given unit displacement only in the upward direction, why not downward, because that is actually equal to the convention of the sign what you have assumed here. then you can have subsequent doubt that why I have assumed the degree of freedom top, you can always assume it bottom also, no problem. Okay, be consistent. So, for the assumed direction give the displacement. Okay. So, bring it down. This effect will also transfer here back. Okay. This is an element of structural mechanics, we already know this. This moment is readily available in the literature, we need not have to memorize this, but we can remember this easily. It is 6E delta by L square. Delta is unity, I may not write delta henceforth, and same value 6E delta by L square. Now I have got an anti-clockwise couple which is 12E delta by L square. I want to find the reaction which is going to oppose this. So, this is anti-clockwise. So, I should say clockwise couple, because this couple will give me a clockwise value which is going to result counteractive to the existing anti-clockwise. So, I should think that this should be equal to 12A delta by L square by L, because L is the distance between the supports, that is nothing but the span of the member. So, 12A by L cube, okay. This is also 12A by L. Okay. Now, this is all about the static balance. So, I have no force in this direction, I have no force in this direction also, which is contributed by the displacement given in the first degree. It does not mean that there are no forces in the direction. For the given system of equilibrium there are no forces. Okay. Now, I want to write the first column of the matrix, which is the first column, which will have 6, because there are 6 degrees of freedom here. Okay, 6 rows and first column. For example, this element will be actually equal to k of 1 1 in my original stiffness matrix. This one stands for the displacement given in the first degree, this one stands for the force in the first degree. For example, this would be k 4 1, this one stands for the displacement in the first degree, whereas this stands for the force in the fourth degree. So, you will obviously see all of them will have a second subscript as 1, being the first column of this matrix. The first subscript will tally with that of the degree of freedom what you have marked in the original figure. So, let us see what is the force in the first degree, which is 12A by L cube, let us say. I am writing positive here because the force is in the same direction as that of the degree of freedom. Since the second degree is upward, whereas the force is there negative, so minus 12A by L cube. Okay. The third degree is clockwise, whereas here the third degree is anti-clockwise. So, minus 6EI by L square. I am removing delta from everywhere, because delta is unity in this case. Okay. The fourth degree is clockwise, whereas the fourth degree also is anti-clockwise here. So, minus 6EI by L square. And this is 0 and 0, because the 5 and 6 does not have any value, whatever may be the sign convention, it is 0. Let us quickly see the unit of one particular value, EI by L cube, Newton per mm square, mm 4, mm cube, you get Newton per millimeter. Okay. You must understand, I have to multiply this with delta, which is also in millimeter. So, I will get force, nothing but all the coefficients of stiffness matrix will give you back only the force units. Okay. I have neglected delta, therefore, that millimeter is not coming there. So, I will get all forces back again. So, this is how simple way to remember how I can derive a stiffness matrix for a given beam element which I studied in mechanics. I will apply the same concept back again here in TLP to derive a stiffness matrix of a TLP. From the same fundamental manner, we will derive the full 6 by 6 matrix. In the possibly next lecture, we will do that. So, by this way you can derive all the remaining columns also, you can complete the full matrix. Of course, there is an order by which you can give this naval notation. We will talk about advanced structure analysis, we will talk about that not in this class, but in some other course later. But there is a simple hint which you can remember easily that if you remember the thumb rule how to derive a stiffness matrix for a simple beam element, same concept can be applied for a TLP derivation here. So that why I am insisting this, because in the coming lectures we will talk about new generation platforms where the geometric conceptualization is still in the concept stage itself, no platform of that order has been constructed. So if you want to really do a research of that order, you have to develop at least the stiffness and mass matrix. You can ask me a question why they are required. If you want to solve the equation of motion, they are required. You can ask me a parallel question again, can I model this numerically in some software and do it? You must check also what are the fundamental frequencies of this. To know that you must have K and M with you, otherwise you cannot check. Okay. So by any roundabout way you must have your K and M matrix with you all the time. You must at least know how they are derived. Then only you can check whether the numerical analysis is giving you the K and M correctly or not. If you know that, then you can always use any other numerical methods like Stodla etc. to find out all frequencies and all mode shapes, and you can compare the numerical analysis like star CCM etc. Then you have a check, double check, yes, my program is correct, learning correctly, my model is right. So any newly developed concept needs lot of rechecking in different stages, for which you must have the fundamental elements of equation of motion ready with you, otherwise you will not be. All the time you cannot depend on modeling them in a software and getting the answers only from the software, which the whole concept cannot be subjected to any rechecking or any revisiting at all. That is not a good idea in research. Okay? So one must have the elements of the equation of motion readily on hand. So we will derive this in the next class for a TLP with the same logic. Now any questions, any doubts here? It is very simple, I mean whatever we discussed so far is fine. So in this lecture we talked about the conceptualization development of deep water platforms from that of shallow and medium, how the geometric design or there is a design concept got evolved from a shallow to deep water, why it was necessary, and what were the prima focus in developing or establishing a conceived idea of a TLP, how they were easily met, and why TLP became successful by making them dominant in many of the international congress today, because of this reason that they have been proven successful. And for an instantaneous let us say statistics which can see in the literature, TLPs have so far not shown any failure structurally. Okay, so far except for one or two they have not shown any structural failure. So it has been, you can always imagine a platform which is conceived for a first time an idea of a swapping meaning has so far not failed at all in its conceptual design. So it has been proved to be a very successful attempt in the whole offshore structural design itself. So that is how TLP became a very important domain of engineering in offshore structural domain. And of course based on this many parallel platforms also came up, which I will talk about later, but the conceptual development grew from TLP and Spark parallelly. Okay, but TLP became very popular because of many advantages I will show you, but we will only here talk about what are the complications in dynamic analysis. The complication will start once you understand or once you attempt to derive K, you will know where the complication starts. It is because of those complications people have stopped doing dynamic analysis in detail of TLPs. That is one of the main reason why, because you will see when I derive K, it is going to be slightly difficult in sense that I will follow the same fundamental logic, will derive, but it will become slightly difficult. Okay. So our job is to make it so easy so you appreciate and understand. Of course there are parallel papers available in the literature which I have referred in NPTEL website, you can see them in advance, you can read them. So next class can be more interesting and more supportive also. Okay.